Bristol Community College, Mathematics with Dan Avedikian, Math 132, Calculus with Applications, Section 15.5, Problem 8. This is Section 15.5, Problem number 8. It says find the area between the function f of x equals x squared shown in red and g of x equals square root of x shown in blue. So just to make this very clear, the square root of x is shown in blue. So g of x, square root of x. And the other one is x squared shown in red. I'll just write x squared. And we want to find the area in between those. So for a problem where you want to find the area trapped between two graphs, you have to set up a definite integral, and you want to do the integral of the top minus the bottom graph. So the top graph, the one that's up a little bit higher, is the square root of x, minus the bottom graph. The bottom graph, the red one, is x squared. And I'll put a dx at the end of my integral. So now to solve this as a definite integral, you need to have the limits of integration, the little numbers on your integral symbol. So that's the point where these two graphs intersect. So one of the points of intersection is at 0, 0, the origin, and then they intersect to the upper right a little bit at, if you read it off the graph, it's over 1, up 1. And it's only the x coordinates that are important. In this case, coincidentally, the x's and y's are the same for both points. But one limit of integration is the x coordinate being 1, and the other limit of integration is the x coordinate being 0. The larger of the two values, the 1, will be the upper limit of integration. The smaller of the two values, the 0, is the lower limit of integration. So the integral that I have to solve has a square root on it. I can't really deal with square roots in terms of the symbol being written into an integral problem. So I'm going to rewrite this as the definite integral between 1 and 0. Instead of square root of x, x to the 1/2 power. And the minus x squared can stay. Put it in parentheses, put a dx on the end. So here's a definite integral. If I solve the definite integral, I'll have the area trapped between the red and the blue graphs. Now to solve any definite integral, it's a 4-step process. Step 1, I want to actually solve the integral. So the x to the 1/2, I'm going to have 1 over 1/2 plus 1, x to the 1/2 plus 1. Usually I don't write the whole thing out when it's a whole number. Like the next one, I just do minus 1 over 3x to the 3. But where I have a fraction, or if it's a negative or a decimal, I'll write out more. So instead of 1/2 plus 1, let me write that as 1 over 1/2 plus 2 over 2. Because the 1 I'm going to change to a 2 over 2, so I'll have a common denominator. And I'll do the same thing in the exponent, x to the, instead of 1/2 plus 1, 1/2 plus 2 over 2. Then the other piece, 1/3 x cubed, can stay. Just make sure you remember that it's a minus. And let me simplify this messy looking fraction that I have here. So I'm going to have 1 over 1/2 plus 2/2 is 3/2. X to the, same situation, 1/2 plus 2/2 is 3/2. And then minus 1/3 x cubed. So this is better, but I have a fraction in the denominator of a bigger fraction. So to clean that up, what I'm going to do is flip that or invert it. It'll come up as 2/3, get multiplied times the numerator, so times 1. 2/3 times 1 is 2/3. So the solution for my integral will be 2/3 x to the 3/2 minus 1/3 x to the 3rd. Notice the fraction that's the exponent did not need to be flipped because it wasn't in a denominator, but the exponent that was in the number in front, or the coefficient, did need to be flipped because it was in the denominator. There is a plus c with this, of course, because it's an integral, but that will cancel by the time I get to the last step, so I don't really bother to write the plus c. So I've solved the integral. The standard notation, I'm going to put a long vertical line to the right of that, put in my limits of integration, +1 and 0. And now I've completed step 1. I've solved the actual integral. Step 2 is I'm going to put in the upper limit of integration into my result for the integral. So the 1 goes in for x. So 2/3 x to the 3/2 will become 2/3 1 to the 3/2. Then minus 1/3 x cubed becomes 1/3 1 cubed. So 1 to the 3/2, 1 to any power just stays 1. So 1 to the 3/2 is 1 times the 2/3 in front is 2/3. Minus, then I have 1/3 times 1 cubed. The 1 cubed is 1. Then 1 times the 1/3 in front is 1/3. Don't forget it's a negative 1/3. So I have a common denominator. 2/3 minus 1/3 is 1/3. So that's the result of evaluating the upper limit of integration, +1/3. Now I'm going to plug in the lower limit of integration for x, which would be very easy. I'm going to get a 0. I'll have 2/3 x to the 3/2 will become 2/3 0 to the 3/2 minus 1/3 0 cubed. It's just 0. And now the last step is subtract the 1/3 I got from step 2 minus the 0 I got from step 3. Because of the 0, the math is very easy. 1/3 minus 0 is 1/3. So the area here trapped between the red and the blue graphs is an area of 1/3.